Today we're going to talk a little bit about gearboxes, and this comes as a special request from Laura at FRC Team 4802, the Unidentified Moving Machines. She wanted to know a little bit about gearboxes, and so I'm gonna try and explain them as best as I can. What is a gearbox? Why do we have them? How can we use them? And how can we calculate what's going on inside of them? As well as, what about the big complicated gearboxes that have like a bazillion gears? We'll explore them all in the course of this video. A gearbox, put simply, is a box of gears. The gears are often arranged so that the speed of a shaft can be increased or decreased, and that has a hidden side effect of increasing or decreasing the torque, and sometimes we can also change the direction of the shaft. So those are the three reasons we have gearboxes: speed, torque, direction. How do we use them? Well, first we've got to understand how power works in a rotary or mechanical sense. Power is the speed of the shaft in radians per second multiplied by the torque in Newton meters, and that gives us the power in watts. Here's the really powerful thing about a gearbox. The input power equals the output power. Now this comes with a small footnote of you do get a little bit of a loss inside the gearbox due to friction, and that heats things up and stuff, so we won't worry about it. For the purpose of this video, input equals output, and that's like the number one take home for power. Power is input and output, they must balance. And so on the concept of balance, we know that the power is made up of speed and torque, so the input speed and torque has to equal the output speed and torque. We can probably assign some numbers to things now, just as a hypothetical gearbox. If we've got 100 watts going in, we've got to get 100 watts coming out. And so let's say that we've got a large motor that has a heck of a lot of torque, but it spins very slowly. We get 2 radians per second as a possible shaft speed, and we have 50 Newton meters as a possible torque output from this motor. And let's say we want to speed the gearbox up. Well, we can speed it up 5 times. That means that the shaft now spins at 10 rads per second, but it also means that the torque goes down by 5. If one thing goes up, the other's got to go down. That's just how it works to maintain that balance or that equilibrium. The left-hand side of this equation has to balance or equal the right-hand side. So we can see 2 times 50 is equal to 100, and so is 10 times 10. The next portion of the video is going to show how different gears actually interact with each other inside the gearbox. The big idea here is that small gears can move large gears, and the small gear will spin quickly and the large gear will spin slowly. On the flip side, large gears can be driving the smaller gears, and that means that the large gear moves slow and the small gear moves fast. So here we are in Fusion, and I've created a little mock-up gearbox with 2 gears, a red and a blue gear. The red has 24 teeth and the blue has 48. And I've just put some little dots on each side so that we can see, as I crank one gear around, we can see how far the other one's gone. And so with a 24 to 48 ratio, that translates to a 1 to 2 ratio, at least for the torque. In terms of the number of rotations, it's actually the other way around. The red gear, if we're spinning the red gear around, the blue one will rotate only half as many times as the red one. So this will do 2 revolutions, and here's 1 revolution, and we can see that the blue one's only turned around half a revolution. If we continue driving it around, we can see that it took 2 revolutions of the red gear to do 1 revolution of the blue gear. And so that's what's called a 2 to 1 ratio. And the way how we can manipulate this ratio is by changing the number of teeth in the gears. So if the red gear were 12 and the blue were still 48, it would actually become a 4 to 1 ratio, so we'd have to crank the red gear 4 times around. And yeah, that's assuming that we're driving the red gear here. Let's suppose that we're using the blue gear as the driver. We can actually get this 2-to-1 ratio to be 1-to-2. So as we rotate the blue gear around, we've gone 1 revolution, and we've seen 2 revolutions of the red gear. And so that's how the gear ratios work. The amount of power, let's suppose that my mouse doing the actual driving here were a motor. The actual power in and out doesn't vary. It's just the speed and the torque that varies. So because the power in equals the power out, if one thing changes, the other one has to change to compensate. So if we change the speed, the torque has to be changed to compensate for that. So for the more complicated gearboxes that you might see, like what we saw in the lathe picture earlier actually, is that we saw one gear driving another, and then that gear was attached to a third gear, and that third gear then drove a fourth gear. And the way how we calculate the ratios for this is we literally multiply a bunch of smaller ratios. So we saw in that previous example of a 1-to-2 ratio, well, let's say we had that exact same setup all over again, but we then doubled it so that 48-tooth gear was then driving another 24-tooth gear on the same shaft, and then that 24 was driving a second 48. So we've got a 1-to-2 that drives another 1-to-2. We just multiply those two ratios together, so we've got a half times a half, that equals a quarter, and that's what we can see here. So back in Fusion, and I've created another gearbox. Well, I've actually just added to the first gearbox. We've got the original red, the original blue. I added a gold and a silver, but it kind of looks like white in this light, gear. And so we've got our original 24 and 48 tooth gears. Then I added a second 24 and a second 48 tooth gear. And what I did is I mounted this golden gear to the blue gear here so that they were going to be locked together. And what I want to do with that is I want to highlight that the ratio between the gold and the silver gear is the same as what we saw between the red and the blue gear, but when we put the red and the blue in combination with the gold and the silver, we get a different ratio come out, like a different total ratio. So if the first ratio was 2-to-1 and the second ratio is also 2-to-1, what would the result be? And the answer is actually 4-to-1, and the reason for that is because this gold one is turning the silver one around at half the speed, but because this brass one, the golden one, is already turning at half the speed of the red one, what's half of a half? It's a quarter. So there's our 4-to-1 right there. And to see it in action, I'll just start turning the red one around. And so let me try turning it clockwise. So turning the red one around one rotation, and we can see the dot here, and there's going to be a dot under here as well, has gone a half a rotation for the middle gear. And we actually call this an idler because it idles there. The red one is driven, the red one is the driver, and the silver one is the driven, and the idler sits in the middle. And often, sometimes you just put an idler in to reverse the direction. One of the things that we noticed is if the red one turns clockwise, the blue one turns counterclockwise, and then the silver one turns clockwise again. And let's suppose that we didn't want an additional gear ratio in there, we just wanted this 2-to-1 reduction. We can easily say, oh, okay, I'm just going to put one more idler in to change it and ignore like the result, because well, I'll get to that in the next slide actually, because there's a neat little formula for just how to figure out idlers, and the number of teeth doesn't matter. But yeah, the red gear has turned around once, the blue gear has turned around a half, and then the silver gear has gone clockwise, but it's only gone clockwise by one turn, by 1/4 of a turn. If I keep turning this around, this is now done 2 turns, and the blue gear has done its complete revolution. It's done one whole revolution, and so that one whole revolution drove the silver gear another 1/4 of a turn, and that's just because of how the ratios stack up. Just keep on turning it around. 3 turns of the red means 3/4 of the silver, and then 4 turns of the red, whoops, a bit too far. 4 turns of the red brings everything back in line. And this works in reverse as well. If we had a motor attached to the silver gear, we can be turning the red gear at 4 times the speed. In fact, it's probably going to be turning, it's turning too fast for my computer to keep up, because, well, my computer's not very good at doing this sort of thing at the moment. That's compound gears. I guess the important thing to think about with idlers isn't so much a nice neat little formula, it's just that they don't change the ratio, they only change the direction.